Network address translation, commonly abbreviated as NAT, is a mechanism that allows one or more private IP addresses to be mapped to one or more public IP addresses. It operates at the boundary between a private network, such as a home or corporate network, and the public internet. NAT is implemented in routers and firewalls, and it plays a central role in how modern networks function, especially in the context of cybersecurity and network architecture. To fully understand why NAT exists, you first need to recall a key concept from your earlier work on subnetting and routing: IP address space. The Internet relies on Internet Protocol version 4 addresses, which are 32-bit numbers typically written in dotted decimal notation such as 192.168.1.10 or 10.0.1. The total number of unique Internet Protocol version 4 addresses is approximately 4.3 billion. As the Internet grew far beyond initial expectations, it became clear that 4.3 billion addresses were not enough to assign a unique public address to every single device in the world. This is called the address exhaustion problem. To solve this problem without immediately replacing the entire Internet infrastructure, NAT was introduced alongside a concept called private address ranges. Private address ranges are blocks of IP addresses that are reserved for internal use within private networks and are not routable on the public Internet. These ranges are defined in a standards document called RFC 1918, and they include 10.0.0.0 to 10.255.255.255, the 10.0.0.0 out of 8 block 172.16.0.0 to 172.31.255.255, the 172.16.0.0 out of 12 block 192.168.0.0 to 192.168.255.255, the 192.168.0.0 out of 16 block. Any device on a private network, such as your laptop, your phone, or a server inside a company, can be assigned an address from one of these ranges. Because these addresses are not routable on the Internet, multiple different private networks across the world can reuse the same private addresses without conflict. For example, both your home router and a corporate office in Tokyo might use the 192.168.1.0 out of 24 range internally, and that is perfectly fine, because those addresses never appear on the public Internet. NAT is what makes this possible in practice. When a device on a private network wants to communicate with a server on the Internet, the NAT-enabled router intercepts the outgoing packet and replaces the private source IP address with its own public IP address before forwarding the packet to the Internet. When the response comes back from the Internet server, the router receives it, looks up which internal device made the original request, and forwards the packet to the correct private device, replacing the destination address back to the private IP. This process is transparent to both the internal device and the external server. The external server sees only the router's public IP address, never the private addresses of the devices behind it. The most common form of NAT used today is called port address translation, sometimes also referred to as NAT overload or many-to-one NAT. In port address translation, a single public IP address is shared among many private devices simultaneously. To keep track of which internal device each connection belongs to, the router uses port numbers. When an internal device with the private address 192.168.1.10 sends a packet to an external web server on port 80 Hypertext Transfer Protocol, the router might assign it a temporary source port such as 52,341 and record the mapping. Internal address 192.168.1.10 on port 49,200 maps to the public IP address 203.0.113.5 on port 52,341. If another internal device at 192.168.1.11 simultaneously connects to the same external server, the router assigns a different temporary port, say 52,342. The external server receives two connections, both appearing to come from 203.0.113.5, but on different source ports. When the responses come back, the router checks its table and routes each reply to the correct internal device. This mapping table maintained by the router is called the NAT translation table. Each entry in this table typically contains the internal, private, IP address and source port, the external, public, IP address and the translated port, the destination IP address and port, the protocol used, transmission control protocol or user datagram protocol, a timer, so that unused entries are eventually removed. Let us walk through a concrete example to make this crystal clear. Suppose a user on a private network has the address 192.168.0.5 and opens a browser to visit a website at public IP address 93.184.216.34. A well-known IP, for example, .com. The browser initiates a transmission control protocol connection on destination port 443, Hypertext Transfer Protocol Secure. The source port chosen by the operating system is, say, 50,100. The packet leaving the user's machine looks like this. Source IP, 192.168.0.5, source port, 50,100. Destination IP, 93.184.216.34, destination port, 443. The NAT router receives this packet, creates a translation table entry, and rewrites the packet. Source IP, 88.12.45.67, the router's public IP, source port, 60,001, a new mapped port, destination IP, 93.184.216.34, destination port, 443. The web server at 93.184.216.34 replies. Source IP, 93.184.216.34, source port, 443. Destination IP, 88.12.45.67, destination port, 60,001. The router receives the reply, consults its NAT translation table, finds that port 60,001 maps to internal device 192.168.0.5 on port 50,100, and forwards the packet accordingly. The user's browser receives the reply as if no translation had occurred. Beyond port address translation, there are other forms of NAT worth understanding. Static NAT creates a permanent one-to-one mapping between a private IP address and a public IP address. This is used when an internal server, such as a web server or a mail server, needs to be reachable from the internet under a fixed public address. For example, a company might permanently map internal server 10.0.0.5 to public address 203.0.113.10 so that external users can always reach it at that public address. Dynamic NAT works similarly to static NAT but uses a pool of public IP addresses rather than a fixed mapping. Internal devices are assigned a public IP from the pool on demand. Once a session ends, the public IP returns to the pool and can be reused. This is less common today than port address translation but was used when organizations had a block of public IPs to manage. From a cybersecurity perspective, NAT has important implications. First, NAT provides a form of implicit security by hiding the internal network topology from the outside world. An attacker scanning the internet cannot directly reach an internal device using its private IP address, because private addresses are not routable externally. This concealment is sometimes described as an accidental firewall effect. However, it is critical to understand that NAT is not a firewall and must not be treated as a substitute for one. NAT controls address translation but does not inspect packet content, does not filter traffic based on rules, and does not protect against malware or malicious connections initiated from inside the network. A device behind NAT can still be compromised if it makes an outbound connection to a malicious server, or if it downloads infected content. In penetration testing and network reconnaissance, understanding NAT is essential. When you scan a network from the outside, you interact with public IP addresses. The devices behind a NAT router are invisible to your external scanner. To map the internal network, you need to operate from inside the network or exploit a vulnerability that gives you access to an internal machine first. Tools such as Nmap, which you have already encountered, will only reveal what is exposed on the public side unless you have internal access. NAT also has implications for network protocols that embed IP addresses inside their payload data. Protocols such as the File Transfer Protocol in active mode or the Session Initiation Protocol for voice communications embed IP addresses and port numbers inside the application data itself. Because NAT only modifies the IP header and transport layer ports, it does not automatically fix these embedded addresses. Special modules called application layer gateways are sometimes used in NAT-capable routers to inspect and rewrite these application-level addresses, but this adds complexity and can sometimes cause connectivity issues. In the context of Internet Protocol version 6, NAT is theoretically unnecessary because Internet Protocol version 6 provides a vastly larger address space, approximately 340 undecillion unique addresses, meaning every device in the world can have a unique globally routable address. However, in practice, NAT with Internet Protocol version 4 remains extremely widespread because the transition to Internet Protocol version 6 is still incomplete, and many networks, especially corporate and home environments, continue to rely on Internet Protocol version 4 with NAT. To summarize the key points of this chapter, NAT maps private IP addresses to public IP addresses, allowing many devices to share a single public IP. Private address ranges, 10 XXX, 172.16 XX to 172.31, XX, 192.168.x.x, are not routable on the Internet and are used inside private networks. Port address translation is the most common form of NAT, using port numbers to track multiple simultaneous connections behind one public IP. The NAT translation table records the mapping between internal addresses/ports and the external address/port combinations. Static NAT provides a fixed one-to-one mapping, typically used for servers that must be reachable from the Internet. NAT provides some degree of topology hiding but is not a firewall and does not replace proper firewall rules. Protocols that embed IP addresses in their payloads may require special handling, application layer gateways, to work correctly through NAT. In penetration testing, NA means that external scanning only sees the public-facing IP, not the internal devices. Understanding NAT is fundamental for anyone working in network security, system administration, or application deployment. When you deploy an application in a containerized environment, configure a cloud infrastructure, or set up a virtual machine lab for penetration testing, you will encounter NAT at every step. Knowing how addresses are translated, where connections break, and how to trace traffic through a NAT boundary is an indispensable skill for a cybersecurity professional.